and somewhat unintuitive. It just run you through the first part of the example again. So there is an asymmetry here in that we have the CNF, but we don't have any terms initially, any cubes initially. And back all the way. Okay. So we want to propagate cubes terms here as well, but at the beginning, we only have the clauses, right? And so we have to have some way of obtaining terms that entail the CNF and that allow us to reason about the strategy of the universal player, right? Or capture all of the potential moves that the universal player can make. And so here at this point, we've just propagated clauses, made decisions, and now we end up at an assignment that satisfies the matrix, right? And we could just take, so we'll just take this as our initial term, and we'll add it to, or we'll take it as a starting point for conflict analysis. We could also add that term to our term database, but typically it's not going to be, so it's going to be weaker than the one that we'll derive using this consensus rule, right? So whereas we have the CNF from the very beginning, the model generation rule will help us derive terms one by one. And indeed, that's really sometimes not the most efficient way of doing it. Just very briefly, in this case, we've propagated, we've assigned by decision, we end up with this satisfying assignment. And that will be the starting point for term learning. So getting this term is called model generation. And then we apply these rules to get a slightly better term that then helps us flip a decision that we made for the universal player. And initially, we only have this one term, right? We would want to, later we'll have terms that propagate units or propagate universal variables. And then we can make consensus steps. But at the beginning, we only have this one term, so there's nothing that we can do except for applying existential reduction to get this term, right? And so now we have one term that we can use for propagation here. And then we end up at a new satisfying assignment, and we'll use that as a starting point for term learning. So I'll skip this remaining part now and show you an alternative to model generation. Maybe then it's more clear, or in any case, the alternative that I'm showing you, I think, is a better way of doing this. Okay. So what ends up happening in practice, and that's exactly what Ardix was getting at, I guess, is that if you use this model generation rule, you have these very long terms, essentially an entire satisfying assignment that you're starting from in your conflict analysis. And then also the terms that you can derive will be very long. And long terms, just like long clauses, cause somewhat of a slowdown in propagation. You have to find the watch literals every time. You don't want many long terms in your term database. And you could try and one thing that people have tried is to derive smaller terms by solving a hitting set problem, because you can think of as these initial terms as hitting every clause, satisfying every clause. So you find a literal that satisfies each of the clauses, and then finding a minimum number of such literals is a hitting set problem. But that's a hard problem in itself. That's an NP-hard optimization problem. So you don't want to solve it every time you reach a satisfying assignment in quantified CDCL. What you want to do instead is, assuming that you have an original formula, QBF, that's in premix normal form, rather than already premix conjunctive normal form, you want to convert to CNF in the way that I showed for PCNF generation, and convert to kind of a dual DNF representation at the same time, and then use the CNF, the clauses, as your initial clauses in quantified CDCL, and use the terms that you derived, the DNF, as your initial terms for quantified CDCL. And then everything is really symmetric. So illustrate that with a simple example. Let's say we have this circuit, so that's our matrix, and this is our quantifier prefix. So we have for all u exists E, for all W, and then that's our matrix right there. But first, we're going to generate CNF in the way that I showed earlier. So we're going to introduce auxiliary variables, one existential variable for each gate, C1, C2, C3, Z, and let's say Z is the variable corresponding to the output gate. Then we're going to add the clauses that make sure that in any satisfying assignment of the set of clauses, these new variables get exactly the values that the gates have that they correspond to. I'm not going to go through that in detail. We had an example of that before, walked through an example before. And then at the very top, we're going to say, oh, and the variable corresponding to our output gate, that has to be true. Right? And now for obtaining initial terms, we do the same thing, but for DNF. So what we want to have is a set of terms that make sure that a set of terms and a set of universally quantified variables, x1, x2, x3, and x, such that the universal player, in order not to lose, in order not to satisfy a term, always has to assign these variables so that the values of the variables correspond to the values of the gates under an assignment of the original variables, Q, E, W. Okay? So for instance, for this AND gate here, we introduce a universally quantified variable x1 and these terms down here. And what do these say? Well, okay, what are the inputs here? If U is assigned false, let me check. So if U is false, then this literal disappears from the term, right? This is true. So we end up with the unit term x1. And so for the universal player, or for propagation not to satisfy this term, this variable has to be assigned false, which is exactly what we want in the case where U is false, right? We have the AND gate says U is an input of that AND gate. So if U is false, the value of x1 has to be false. So this is what this term here achieves. Similarly here, if E is false, then again, we get a unit term, x1, and so x1 has to be assigned false for this term not to be true. So that's what propagation will do for terms. And then finally, we have this term here. And this says, okay, if both of these are true, both of these literals will disappear, and we end up with the unit term, not x1. And so for the universal player not to satisfy this, we have to assign x1 true. Okay. So what this set of terms achieves is that by propagation, x1 will always be assigned so that its value corresponds to U and E. Okay. And we do the same thing for the other gates. Introduce some more terms here. And these terms achieve that universal is forced to assign these new variables so that the values correspond to the gate values. And then finally at the top, we have now a unit term which says that, oh, and in addition to that, the circuit has to output false, right? That's what we want. As a universal player, we want to falsify. So this set of terms guarantees that the universal player has to play in such a way as to assign these auxiliary variables so that they correspond to the gate outputs. And then they also have to make sure that the output is false, right? Okay, so, and that's typically a better way to initialize your terms than just using model generation and deriving them one by one. Because here it's completely symmetric, and you get shorter terms in most cases. Okay, now what remains is the question of where to put these levels, the quantifications of these variables in the quantifier prefix. And one way of doing this is just putting them at the very right. And then the relative ordering doesn't matter, right? Whether you put the existentials first or how you order these doesn't really matter. That's what I'm trying to indicate here. Okay, so that's typically a better way to obtain initial terms than using model generation, because you end up deriving, or the algorithm ends up deriving smaller terms from these. Yes?
What if you have a CNF is your original formula, not a circuit?
Okay, so there's one, there is a paper on this, which shows that even if you have CNF, you might want to define auxiliary variables that, one for each clause that that are true if and only if the clause is satisfied, and use these in order to obtain your initial terms. That's a paper by Mikudashi Anota, and shows that even in that case, you can get an exponential speed up compared to just using model generation, because now you have these auxiliary variables for the clauses, and that can lead you to shorter proofs. However, in practice, it typically just slows down the solver a lot, because you need to introduce many terms in order to define these auxiliary variables the right way. So I think, yeah, it's a bit unclear. It can give you a speed up in theory. In practice, if you have a CNF, model generation might be a better choice if you want to run CBCL.
It's better to start from a circuit.
In general, I think it's better to start from a circuit, and that's something that I think has been haunting the community for ages, that people started from CNF specifications and write CNF QBFs, and then it's very, it can make it harder to solve. And people, because it's so common in SAT, tend to write their encodings in CNF. And even though it would be preferable in many cases to start from a circuit, yes.
Thanks. Yeah.
Okay, one short slide explaining why we have this restriction on the decision variables that we can choose when we get to a decision. So what I said earlier was, if you're at this point here, so you've propagated, you haven't encountered a conflict or a satisfying assignment, then you have to make a decision. And what the rule I suggested there was pick a variable, or the restriction rather, is you have to pick a variable from the leftmost quantifier prefix that still has unassigned variables. Let's ignore that for the moment and just choose a variable from some other quantifier block. So here, let's start with E3, which is in the last quantifier block. Then this clause becomes a unit clause. We propagate E2, and we end up with this clause. Now we start performing Q resolution in order to derive a new learn clause. We get to this clause here, U and E3. And now we can't really continue, right? Because we don't have, yeah, we've resolved on E2. E3 is here. It's assigned, but it wasn't assigned by propagation, right? It was assigned by a decision. So we can't resolve this out, but we also can't apply universal reduction because, because U comes before E3 in the quantifier prefix, okay? And that's a clause that doesn't do anything by propagation if we backtrack, right? Because U is not assigned at this point. If we now backtrack, this clause will not become a unit clause, and so it won't keep us from assigning E3 false by decision, right? So here we get stuck in a way, and we don't get an asserting clause. Now, there are different suggestions of dealing with this. One is to use so-called dependency schemes to give you a sort of a sound way of making decisions in a more relaxed way. So relaxing this order in a way where you can be sure that you can still always derive an asserting clause. This was implemented in a solver named DepQBF. Me and colleagues from Vienna, we tried to come up with a kind of a lazy alternative to this where we start out ignoring these restrictions, and then only when we run into a situation like that, we'll add a temporary restriction saying, okay, well, let's not assign E3 before U for the moment, because otherwise we might get stuck in the search. And then there was another paper on this recently where the authors tried to live with the fact that they don't get asserting clauses here. And just say, okay, well, then in our propagation rules, or rather in our decision rules, we have to make sure that if we have a clause like that, we don't assign E3 false by decision. So we kind of have to monitor our clauses more closely in order to make sure we don't make the wrong decision. Okay, now that's just what I showed you was one way of defining QCDCL. You can come up with different flavors, so to speak. You can add universal reduction to your propagation rule, which will give you a stronger form of propagation. Then, however, you need to use a different proof system for conflict analysis called long distance Q resolution, which is a bit weird because you get superficially tautological clauses, and that confused people for a while. It's okay to do it, but it's a bit strange at face value. So that's actually one of the early papers on quantified CDCL. The authors realized, oh, if we just do conflict analysis in the SAT way with propagation that uses universal reduction, we end up with these tautological clauses, but they're kind of okay. They don't cause any issues. It didn't really prove its sound. But they had some argument, to be fair, but I think kind of a proper soundness proof of the proof system only came quite a bit later. You can also use, have a version of that where you, even though you have the stronger form of propagation, you still get a Q resolution proof by, kind of finding a different proof after, during conflict analysis. That's called QPUP learning. Then something I tried a while ago was also propagating in clauses, propagating universal variables, which is kind of weird if you think about it, but turns out from a proof theoretical perspective, that can sometimes make help you find shorter proofs. Then you get a proof system which is essentially Q resolution with the only change that you can also resolve over universally quantified variables. Okay. So what hasn't been done is switching between universal reduction and propagating universal unit clauses, which might also, be a possibility. Okay, so what are some challenges that remain? I think really the main one is that QCDCL gets stuck learning long terms. I don't know, maybe some of the ideas that are implemented in your paper might help with that, Alex. I think that's certainly something to explore. I think there are a couple of works now on click-sync DNF generation, or at least I've seen the titles of works that might be useful here as well. So I think generating terms in a smarter way might make a big difference here. Then I'm not going to talk about this, but many standard CNF preprocessing rules you can sort of lift to QBF, and this has been done in preprocessors. What hasn't been done is also using this as in-processing rules. So stopping at a certain point in your QCDCL algorithm, taking the set of clauses you've already derived, and then applying preprocessing rules to simplify your database. That could be done for QCDCL as well. It's just that somebody has to do it, and I think it's a lot of work. And that what we also saw in experiments for that paper on dependency learning was that sometimes if you have no restrictions on your decision order, that can actually be detrimental for performance, even though in principle it feels like you shouldn't be worse off by having more freedom in your decisions. But then we don't really have any bespoke decision heuristics for QBF. We were just using VSITs, and so maybe that's not the best way of going about this, and one should assign some QBF-specific heuristics instead. Okay, so this I'll leave for tomorrow, and I will now go to the hands-on session. Just I think it would be better to skip ahead because this is at the very end. Yeah. Okay, what I thought we'd do here is you just take your laptops, and I put together a small little website with links to benchmarks, also a Python interface that you can use and that you can play around with. And then I also have some suggestions for or explanations of how you can use these things. I don't know. What's that? Oh. Well, you don't take a picture, you just point the camera, technically. I hope that's fine. I don't know. Or you just type in the URL, sorry. It's not that long. A good point. I didn't think about this being a security issue. Maybe I can even, sorry. Maybe I should open the website and show what's there, just real quick. What? I want to go to GitHub. Is that an option? Can I look at the website? Okay, no. Okay. Well, briefly show what's on the website. No, the GitHub repository. Just for the website, on the GitHub website itself. Yeah. In the meantime, you can try and compile some of these QBF solvers and tell me how many bugs you encounter. Just trying to compile them. Oh, I do have my own laptop, yeah. Yeah, sorry, already small bugs encountered. Oh, but yeah, oh, great, yeah, okay, awesome. How do I scroll here or just on the? So here are a couple of suggestions of things that you can do. There is a formula generator, which is used to generate classes of formulas that tend to be hard, like slightly artificial formulas that tend to be hard for certain classes of solvers. You can download that. You just need Python for that. You can generate some instances. The interface is, command line interface is fairly easy, and you can, they all have a parameter n that you can use to sort of make them harder. So one example I had, can I switch back and forth between the slides and this easily, or? Okay. So for instance, you can generate a formula from a famous class of formulas called the, named after kleine Bühne in Krapinski and Flögel. That was the first class that was kind of argued to be hard for Q resolution. So there are no short Q resolution proofs of these formulas. Therefore, if you run a version of quantified CDCL that generates Q resolution proofs, it will take a long time to solve them for larger numbers of n. And so here, this assuming you're in the directory, generated directory, would generate an instance for n equals 10. And then you can solve it using a solver like DebQBF, which I think should also compile on Mac, for instance. And then you can try larger values of n, specifically for DebQBF, and see what happens there. No, it's good. Yeah, I've just, yeah. Okay, so this is a class of formulas that's, oh, yeah, you have a question? Can you get? Or can you get the mic?
Is it there? Okay. I just wanted to ask, where is this qbffam.py in the repository? I did not find
The what file?
this Python file, the for the formula generation.
Oh, oh, it's not there.
And the
Sorry, it's
first,
just it's linked in the README at the top. You see? For the QBF, this file.
oh, okay.
Yeah.
Thanks.
Okay, I'm just going to go through this briefly. So this is an instance that's hard if you run depqbf without any parameters, without any specific options. N equals 10 will be solved fairly quickly. Then once you go to n equals 20, going to probably run forever. But if you use a different version of propagation, which is the one that uses universal reduction, and this long distance Q resolution proof system will actually be able to solve these instantly, even for large n. Just a little bit more explanation about these links here. So there are some benchmarks you can download here. First two are sets of benchmarks that are in Phoenix conjunctive normal form. So their file format is called QDymex here. The third and fourth, the last two here, these are in Phoenix normal form or a Phoenix normal form representation, and the standard is called QCIR. Then you get you have solvers that can handle one or the other or both input formats here. So Cake here is the one that, together with pre-processing, did the best in the last QBF evaluations that were run while this was still under development. depqbf is another one that one is CDCL based. We'll talk about the techniques underlying Cake tomorrow. Qt is another QCDCL based solver. And Quest we'll talk about tomorrow as well. Okay. And then there are some circuit solvers, and Qt here is using, so for the circuits, Qt is initializing clauses and terms in just the way that I explained earlier. Then there are a couple of preprocessors, or the two preprocessors, Blocker and HQS pre. So these only apply to CNF input, but they're very powerful. So in many cases, the preprocessors, if you have a QDymex, a Phoenix conjunctive normal form instance, will be able to solve such a formula on its own. And then there's a bit about proofs and expecting strategies. I have a small Python wrapper here for depqbf with an interface so there's Python SAT. Not quite as convenient here, but I tried to write something quickly that you can use. So somebody already told me this is not download requirements, but what should it be? Download dependencies? Yeah, okay. And then you can do things like add a quantifier prefix and add clauses, and then solve the QBF. And in case you have a false QBF, which if you have a false QBF and the first quantifier block is universal, then you can extract an assignment of the universal variables, which corresponds to the winning strategy using this command here. Okay, so let me show you a few more things you can try. Maybe after is better. I don't know. So you can try and use a tool for reverse engineering pre-next normal form from a CNF formula. So if you only have the Q dimex instance, in certain cases, you can reconstruct the original circuit. And this is based on kind of undoing the transformation I showed you earlier, where you introduce these auxiliary variables. The one option is if you have a Q dimex PCNF formula, you can just solve that using a solver. So my own solver is not going to do well on this instance. But if you run circuit reconstruction first and type the output to the solver, then it can start from a circuit, get smaller initial terms, and it's able to solve that formula fairly quickly. As an alternative, instead of obtaining this QCIR instance, you can apply preprocessing to the PCNF formula, and for instance use this blocker preprocessor, simplify the CNF formula to get a smaller CNF formula, and then pipe that to the solver. And then again, in this particular case, which is an instance from the first set, you can solve that quickly. Do you have a question back there? Yeah, can you get the mic? Oh, sorry, did we just, no. HQ3, good point. It works both on dependency QBF and on QBF. It can do both. I think it implements pretty much every preprocessing rule for QBF and DQ. I know of, at least. Here's one more thing you can experiment with. You can write down a simple PCNF formula in the Q dimex format. So if we take this PCNF formula, which says there exists E, that for all U, well, E and U are equivalent. That's clearly false. And the universal winning strategy is just to assign U to. You can write that as a Q dimex formula or a Q dimex file, like so. Starts with this preamble here, PCNF, which is like in dimex file, and then you have the maximum variable index that's occurring, that's 2, and 2 clauses in this case. And you write, so the first quantifier block is an existential quantifier block, write it by starting the line with E, then separated by spaces, you have variables that are in the quantifier block, and then this is 0 terminated. Right? E stands for existential, yeah? And A stands for all. Okay? So yeah, you introduce 1 existentially quantified and 2 universally quantified. And then you have these 2 clauses. So 1 and minus means negation, 1 and not 2, sorry, 1 or not 2, not 1 or 2. Okay? So that's this QBF as a Q dimex file. And then you can use step QBF to generate a refutation in essentially a Q resolution refutation. But you need to use certain, so the crucial part here is that you write, sorry, I think this should be double dashes here, trace equals QRP, and then it will write the trace to standard out. And it will tell you which options you have to set in order for it to be able to generate the proofs. You need some other command lines settings to be on so that it can generate the proof. You can then, type that or write that output to a certain file, to a proof file, and then actually obtain the winning strategy from that proof file. So first, you might want to use a tool which is also linked on the website that makes sure that the trace is correct, syntactically valid. And then you can extract the strategy as an Eiger file, as a circuit that represents the winning strategy for the universal player, using a different tool called QRP-cert, which is also linked. And then you get this Eiger file, which defines a circuit. The winning strategy is a circuit. So 2 is a bound on the variables or the indices that appear in this file. You have 1 input, 1 output, and 1 AND gate. So an Eiger file encodes an AND inverter graph. So it's kind of a slightly restricted circuit, only consisting of ANDs on literals. 1 is the input. The literals here are always multiplied by 2. 1 is the input, 2 is the output, and then the output is defined by it's not 1 and not 1. So the literal plus 1, I guess, is always the negated literal. So this is short for negated 1. And so the output is just not 1. That's what this file specifies. Okay. And then once you have the strategy, as a last step, you want to take that circuit and make sure it really is a winning strategy by substituting the circuit for your universal variable. And then that the resulting propositional formula has to be unsatisfiable. So in this case, you can achieve this by running this command. So formula is the formula you started from that you solved. The strategy is the Eiger file. And then what this does is substitute the strategy for the universal variables and create a CNF file. In this case, this is fairly straightforward because the winning strategy is just for U is to assign the negation of E. And so if we substitute that in the matrix here, we get E or not E, and not E and not E. So that's just E and not E, and that formula is unsatisfiable, right? We want to check at the very end that the CNF formula you get from this is unsatisfiable by running a SAT solver. Yep.
So in principle, your QBF solver already has enough information to know why this formula is unsat?
That's an excellent question. Yeah. So I think also so this goes back to this workflow was implemented by students of Armin. I think in these experiments, sometimes you'd get a timeout solving these formulas. I think that was the bottleneck for some of the large strategies that you couldn't solve these instances. I don't know if this was with different SAT solvers, but I would assume it's still the case. With people from Vienna, we tried to come up with a way of avoiding this by generating the propositional proof of this instance along with the formula that you have to prove is unsatisfiable. Yeah, so in principle, you have that information and you can generate the proof. Whether that counts as the kind of independent validation you want is perhaps a bit questionable, because in principle, yes, but you know, if the tool generates both the formula and its proof, I don't know, maybe it's just, I don't know, maybe it's just a heuristic question of how much you trust that. Kind of need to verify that I guess what you want to verify as well is that the substitution has been done correctly, right? Once you have that, you could use that to.
But that's kind of a syntactic check. So I think
Yes.
verifying that should not be hard.
That's true. Yeah, I think ultimately, I think we had our experimental results also using these generated proofs at the time were a bit disappointing. So I think we were able to do better than solving everything from scratch, but not by that much, not by as much as you would expect. I think there was possibly also an issue with the implementation, but in principle, it can be done. Yes. So if you, specifically for QCDCL, you know, yeah, what the proof of unsatisfiability should be for that CNF formula, and you could just try and validate that. It's a possibility that, oh, okay, yeah, actually, I think at the time we didn't have these more verbose proof formats, so we tried with root proofs, and there I think unit propagation was the issue. Really, well, finding or validating these root steps was somehow because the proofs tended to be very large when the certificate is large, proof is large as well, and there really just the validation of the root proof became the bottleneck. I suspect that with LRET, LROOP, if you can also tell the solver in which, or rather the verifier in which order the resolution steps should be made or the propagation should be made, that it might be easier. But yeah, so that's a long-winded answer of saying yes, indeed, or version of saying yes, indeed, you could do that. Yeah, I don't know how we should proceed here. I could just continue with more algorithms for QBF, or I'll let people work on this. I don't know what's the preference. Because you'll get the slides. You can go through these things slowly. Maybe experiment offline. Certainly encourage that. But since not everybody is doing this, maybe I'll just continue with more QBF algorithms. We'll have about 15 minutes. Or, yeah. Yeah.
We have things like PySat or Optilog or something, which allows us to plug in multiple things.
Yeah.
And do we have similar things for QBF?
I'm afraid no. I think maybe. Well, do you have some? Oh yeah, right. Okay.
Which one?
I can. You look it up.
Yeah, Max Heisinger has like a WebAssembly thing. And if you search for Limbool, you will find this Limbool interface also as QBF
So
on this.
you can specify a formula and run some solver on it?
Yes,
or-
on the web, even on your phone if you want.
On phone, okay. Yeah.
Oh,
But unfortunately, there's not something like Python SAT, which is extremely convenient. So preparing this for okay. Okay, great. Well, yeah. Just need to look this up, yeah, and I'll add it to the slide. But I guess nothing supported natively by the solvers themselves. Anyway, okay, then I'll continue here with a different style of QBF solver that succeeded quantified CDCL. Because people realize that developing a QCDC solver from scratch is fairly, well, takes a bit of work. And instead, you may want to use SAT oracles in a smart way to solve QBF. And I think there's one line of work on this called, that's inspired by counterexample guided abstraction refinement from model checking, and it's also called CGAR solving. And while the sort of the semantics underlying QCDCL is this recursive evaluation, for CGAR, the underlying paradigm is based on expansion, this kind of substitution of, replacing universal quantification in particular by a conjunction, right? We said at the beginning, universal quantifiers you can think of as an abbreviation for a conjunction where you want substitute false for your universally quantified variable and one substitute true for your universally quantified variable. Now, if we take a more restricted Prenix QBF, where we have just one alternation between quantifiers. So we have only two quantifier blocks. The first one is universally quantified. The second one is existentially quantified. We can sort of think of this expansion, this Shannon expansion here. We do all these steps at once for our universally quantified variables. And this is equivalent to a big conjunction over all assignments of the universally quantified variables. And then we have the existential quantification still inside, right? So we have our matrix pi here, and then we just take a big conjunction over the universally quantified variables, plug in this assignment, and then still existentially quantify over these e variables, right? So that's equivalent. But this formula here, you can now turn into a purely propositional formula by renaming variables. And so instead of having these existential quantifiers there in the innermost block here or inside here, you can introduce a separate copy of these e variables, one for each assignment of the universal variables, just like in this motivating example at the beginning, right? So what you can do, and I'm trying to kind of write it down here, this way is you plug in the assignment of the universally quantified variables. So now you're just left with this existential quantification. And instead of the existential quantification, you just replace the existentially quantified variables with a new set of variables that are kind of marked or annotated with the assignment of the existentially quantified variables, right? This tau. So what I mean by this is you take each variable in E, you introduce a new variable that sort of has this tau as a mark. And now you have a purely propositional formula that can be, of course, it will be exponentially large in general. And you can simply, now use a SAT solver to solve this. Of course, but normally you would not want to generate the entire this entire conjunction here. But instead hope that if the formula is unsatisfiable, if this formula is unsatisfiable, already a small set of clauses gives you an unsatisfiable subset. Yes? Mike, please.
So this is a skolemization, right? Or how is it different?
It's in a way it's symbolic skolemization, right? Because we're introducing new Skolem constants, yes, for each of the existentially quantified variables. Exactly, yeah. So we can think of this as skolemization. Yes. And we get now get a propositional formula that's satisfiable if and only if the original QBF was true. And again, the hope is that if we generate this formula kind of successively, not writing down this huge conjunction in one go, but instead generate this in a more controlled way that will be able to arrive at a small subset of clauses that's already unsatisfied. And in order to turn that really into an evaluation algorithm for QBF, you can go back to the game semantics. And specifically for 2QBF, so for formulas where you just have for all exists as in the prefix. So in that case, the game is played by the universal player first assigning their variables, and then the existential picking an assignment for the E variables in such a way that the combined assignment satisfies the matrix. So, and in this case, existential wins if the assignment satisfies the matrix. And now we can try and turn that into an algorithm by just going through all possible moves of the existential player. Right? Start with some assignment, plug in that assignment into the matrix. Now you have a propositional formula again. If that's satisfiable, or if it's unsatisfiable, then the existential player has no way of winning the evaluation game if universal makes that move, right? So in that case, we can immediately say, okay, this QBF is false. The 2QBF is false. If it is satisfiable, then the existential player has some response to this assignment, and the universal player has to try another assignment. Okay, so move on to a second assignment. Can ask the same question here. We plug in that move by the universal player, ask, is the resulting propositional formula satisfiable? So is there a move for the existential player to respond? Again, if that's not the case, the QBF is false. Otherwise, we have to continue. Okay, so if we're lucky, and in particular, if the QBF is false, then there will be some assignment for the universal player where existential cannot respond, and where this propositional formula here will be unsatisfied. And if we're lucky, we can just find that assignment and terminate answering that the QBF is false. However, if you're unlucky or the formula is satisfiable, then running this would force us to go through all assignments of the universally quantified variables. And that may be too large. So in this case, we really have to, if it's satisfied, we really have to run through all assignments. And only after checking all of them, we can finally say, oh, the QBF is true, because existential was able to respond to all moves of the universal player. And that's clearly not, well, ideal in many cases. And so what one can do instead is look at this, okay, look at the first move played by the existential player to respond to tau 1. Sorry, yeah, to tau 1. Right here as well, okay. Now this move, this counter move here, which is the sigma here, or sorry, rather sigma 1, this move for the existential player, this might also work against other moves of the universal player, right? So this, it was obtained as a move specifically against tau 1, but it might actually work against other moves as well. And we want to skip these moves for the universal player, right? So the universal player has seen this sigma 1, and they now should try to find a move so that sigma 1 is not a response for the existential player, right? Because, you know, if tau 2 and sigma 1 still satisfies the matrix, existential can just keep playing that move, and it will, they will still win. So what we want to do is skip ahead to a different move for the universal player, so that certainly, if we combine it with sigma 1, the assignment falsifies the matrix. So the next move that we come up with for the universal player should be one that works against this move from the existential player. And actually all previously seen moves, right? So we've seen some moves from the existential player, I moves. Then for the I+1 move from the universal player, we want to find one that ensures that it works against all of the previously seen moves. And that is the case. Yeah, this conjunction is true, right? We want to find a move for the universal player so that if we substitute the first existential move, then if we combine this with tau I+1, it falsifies the matrix. And it should also falsify the matrix together with sigma 2 and so on until, yeah, we get to sigma I. Okay. What we want to generate for the universal player is a new move that works against everything that the universal player has thrown at them previously. And by maintaining this formula here, we're making sure that this is the case always for our I+1th move, we can ensure that, right? And so now this is called the abstraction in this counterexample guided abstraction refinement algorithm. I think abstraction is a bit of a lofty term there, but I don't know, I've argued a little bit with one of the authors about this, but Mikuláš, who came up with this, maintains that it is a form of abstraction, even though I think it's a fairly simple abstraction compared to what is used in CGAR for model checking. Okay, then I think I'll just run through an example and then stop here, or I have until 5, right? So this was introduced by Mikuláš Janota and João Marques Silva, specifically as an algorithm for 2QBF. So at the beginning, the abstraction is empty, meaning it's just constant while it's true. And then in a loop, what you want to do is generate moves for the universal player by solving the abstraction. So initially, so we ask, is the abstraction satisfiable? And so this will be a truth value indicating whether it's satisfiable, and tau will be a satisfying assignment if there is one. Okay. Initially, the abstraction is, I'm just presenting the algorithm first, sorry. If the abstraction is not satisfiable, that means there are no moves left for the universal player. Everything is already covered by the moves that we've seen for the existential player, right? In that case, the 2QBF is true. If we still have a solution to the abstraction, then we have obtained or can obtain a new move for the universal player. And then the existential player has to find a response. So this is what we're asking here. So tau is our new move. That's the solution to the abstraction. And so we ask okay, can the existential player respond to this? If they cannot respond, then the 2QBF is false, like we argued before. And if they can respond, well, then you add this move to our list of previously seen moves, or rather you add you plug in that assignment of the existential player, or the move played by the existential player, plug that into not phi, and add that to your abstraction. Okay, so here's a simple example to end with. So we have for all U1, for all U2, there exists E such that these clauses are satisfied. Okay, initially, we start by solving our initial abstraction, which is trivially true. So we get some assignment of the universally quantified variables. It could be just U1 and U2. Then we plug that into our matrix and ask if that's still satisfiable. So in this case, if we, so if this is U1, U2, we plug that in here. What's left is, I think, so the first clause vanishes and the third clause vanishes. And then we just end up with E. So by playing E true for the existential player, they're able to respond. And so if we now plug in that assignment in order to refine our abstraction, phi of sigma will be that. So the negation of that, which is what we want to add to the abstraction, is this formula. Okay. Okay, then we go back solving the abstraction. So the solution here would be just signing not one and not U1, not U2. And to that, the existential player can respond by playing not E. And then plugging in not E gets you this this formula here. And again, we negate that and add it to the abstraction. So yeah, the negation of this here is this. Go back to solving the abstraction. This is a possibility. This is a move that satisfies the abstraction. And now if we plug that into our, we plug that into our matrix, we get, we get this. Get this formula here, which is unsatisfiable. Right? Here at this point now, we would say, oh, that's not satisfiable because we have this it glitched. But yeah, we have this formula here that's unsatisfiable, and so we would return false at this point. Okay. Oh, yeah, question?
Are there any, so is this abstraction always going to be a CNF?
Yeah, good question. You have to put in some work to convert it into CNF.
Okay.
So in general, no, because you're adding these negations, right? So you in order to negate the CNF, you typically would want to introduce auxiliary variables. Yeah? So that's something you would have to do to actually use a CNF SAT solver here. Yeah.
Not for free, but so
Yeah.
in this example, because it's a simplified.
Oh yeah, in this case, I think it just
works
happens
out.
to be CNF
Yeah.
by chance. In general, it won't be. It doesn't have to be CNF. Yes.
Thanks.
Yeah, if there are no further questions, I think it's probably time to end, right? What does the session chair say?
And then Arvind will take over. You then have a good night's sleep and then be fresh for tomorrow.
Just again, couple of announcements. Again, I'm here to remind you of the various things that you have to do. First thing, if anyone by chance hasn't collected the registration kit, you are more than welcome to collect it from the help desk that is just outside the MPH today, tomorrow, whenever you find time. Second thing is, we have arranged conference shuttles from the venue to the various locations. The schedule is already on the website. You can check it out. It will be updated as the day goes. I think by 6 p.m. it will be updated. That will be the final version of the routes. The buses will leave in another 10 to 15 minutes. So if you want to commute, just for the ease of communication. One more thing. Sorry, my phone got locked. Yeah, the ID card, the TCS ID card, not the SAT one, not the one with the red lanyard. The TCS ID card that you have gotten, you need to return it at the reception so that you can collect it again tomorrow morning and you follow the routine the whole day. Last but not the least, since the conference shuttles are arriving a little earlier, and if you feel a little hungry in the morning, we have arranged for food in the cafeteria. You can order. There are kiosks available. There are proper, cafeteria services available, so you can have your food in the morning. Thank you, and once again, hope to see you tomorrow.
Okay, and one quick announcement, because your academics, you'd be itching for a board and a pen, okay, a marker pen to kind of go and discuss some things. So since you do not find them here, you should not feel disheartened, because there is another place where there's a lot of boards and a lot of discussion places, and we have whole discussion rooms booked for the entire week. Okay, so this is for a discussion whenever you want to have. So in case you would like to see them, you can come along and you can see the places where you can have extensive discussions and write open problems and so on.